Hi everyone, Harry and I are doing our project on the Briggs-Rauscher's oscillating reaction. Hope you guys enjoy. The Briggs-Rauscher oscillating reaction demonstrates an oscillating chemical reaction involving three colorless solutions. Solution A involves a mixture of potassium iodide and sulfuric acid, while solution B is a mixture of malonic acid and manganese sulfate monohydrate. The final solution is hydrogen peroxide. When three of the colorless solutions are combined together, the resulting mixture produces an oscillation between colors of clear, amber, and deep blue. When the reaction subsides, the final color of the mixture is dark blue. And now we're going to show a video of the oscillating reaction. The second solution is added onto the first solution, and the third solution is added last. And the reaction can now take place. The first color turns into amber, then turns into dark blue. The dark blue color soon fades and turns clear, and the cycle continues again. This reaction is due to the oxidation of malonic acid with hydrogen peroxide. This produces carbon dioxide in water. The amber color is due to the formation of free iodine, while the dark blue color is due to the reaction of starch of free iodine. The oscillation of colors will continue until there are no more malonic acid left. If there are no more malonic acid left, the oscillation of colors will stop and will leave you with a dark blue color. The history of the Briggs-Rauscher oscillating reaction started with the first homogeneous oscillating reaction between hydrogen peroxide and iodide in 1921. However, this reaction between hydrogen peroxide and iodide was not eye-catching due to experimental difficulty. On the other hand, in 1958, B.P. Belousov discovered the Belousov-Zabotinsky reaction. However, at that time, he encountered skepticism as the oscillatory behavior of his reaction was unheard of before. Later, in 1964, the Belousov-Zabotinsky reaction was researched and verified by A.M. Zabotinsky. Furthermore, in 1972, science instructors Thomas Briggs and Warren Rauscher at Galileo High School in San Francisco discovered the Briggs-Rauscher oscillating reaction when articles in the Journal of Chemical Education caught their eye. Briggs and Rauscher replaced bromate in the Belousov-Zabotinsky reaction with iodide and added hydrogen peroxide in the mix. Briggs and Rauscher surprisingly produced a color-changing reaction when a starch indicator was added into the system. Since then, many scientists have further done their research on this unusual chemical reaction.
Non-radical process. The slow consumption of free iodine by malonic acid subtract in the presence of iodate. This process involves intermediate production of iodide ion. Radical process. A fast autocatalytic process involving manganese and free radical intermediates, which converts hydrogen peroxide and iodate to free iodine and oxygen. This process also can consume iodide up to a limiting rate. The iodate ion is changed into iodine by hydrogen peroxide. The color changes into amber.
That's it.
Step 2. The free iodine reacts with malonic acid to produce iodide ions. Step 3. The free iodine combines with iodide very rapidly to form negative ion triiodide, which reacts with starch to form a dark blue complex. Step 4. After a period of time, the triiodide ions are converted back into iodine and iodide ions, so the dark blue color disappears and process repeats itself. Eventually, the faster step 3 becomes dominant, and the change of triiodide back to iodine and iodide stops after about 15 cycles, so the solution remains dark blue. Here's the explanation. As this reaction runs, the relative amount of reactant and product dictates the color of the solution. Triiodide is formed when iodide and iodine interact, and this cycle continues until all the reactants are used up.
this is the color analysis of the Briggs-Rauscher's oscillating reaction. The reaction goes through a cycle of at least 10 times, and it slowly fades to colorless until reaching a dark blue color. The initial condition of the starting solution starts off as an aqueous phase that contains hydrogen peroxide, manganese as the catalyst, sulfuric acid, which is an unreactive acid, malonic acid, which is an organic compound that help with reducing free iodine into iodide. Starch can be added as an indicator to determine the increase in concentration of iodide ion as its color changes from amber to dark blue. However, the presence of starch causes number of oscillations to be greater and longer than starch-free mixtures. It has been thought that the starch serves as a storage unit for the iodide and iodine due to the starch triiodide equilibrium, therefore modifying where iodine and iodide are involved in the process. The reaction is soon taken over by chloride ion and will oscillate a wide range of initial concentrations. The chemical reaction produces gradual and sudden color changes that are visible upon the eyes. Oscillations happen in different temperatures. For higher temperatures, oscillation happens at a faster rate, producing some qualitative changes. Sharp color changes occur due to constant stirring of the solution throughout the reaction. And also bubbles form throughout the reaction, and the final state is rich in free iodine, producing a strong scent of iodine. Now let's talk about the modifications in terms of the reaction. Alternate initial concentration. Changing initial concentration of ions will most likely result in longer cycles in dilute solutions that produce weak color oscillations. Replacing malonic acid. Malonic acid plays an important role in the reaction as it gets oxidized to carbon dioxide. Replacing malonic acid with acetone or acetylacetone have been reported to have distinctive features just as malonic acid would. And fluorescent demonstration. In 2007, Weinberg and Muskin replaced the indicator starch with fluorescent dye instead, and were able to produce a visible reaction under UV illumination. Effects of temperature on reaction rate. There were 4 series of temperature that have been tested to show how different temperature range affected the rate of chemical reaction. The first temperature was 10 degrees Celsius. When the last solution, hydrogen peroxide, was added into the mix, it took a little longer for the mixture to turn deep blue. This is due to the low temperature and limited heat collisions. Now let's see what will happen if we double the temperature. It immediately turned a deep blue color once hydrogen peroxide was added, indicating that an increase in temperature will increase the rate of reaction. Now let's see what will happen at 40 degrees Celsius. Once hydrogen peroxide was added into the mix, it immediately turned amber to clear. This is because the negative I3 was very dominant against the iodine and iodide ions. Therefore, the deep blue was not present because the faster the reaction is due to extensive amount of collision, the faster it is to stop and form a dark blue complex. Lastly, the effect of temperature at 60 degrees Celsius. Once hydrogen peroxide was added in the solution, the oscillation of colors escalated quickly, turning from clear to amber, and this is due to the intense heat and the heat collisions. Since heat was very high, it didn't take long for a solution to turn deep blue.
Here's how it's used in everyday life. It is applied for the measurement of antioxidant pH level of Croatian wine when it's consumed by human body, and is suitable as an analytical method for in vitro determination of relative antioxidative potential of wines at a pH of 2.
This concludes our topic on the Briggs-Rauscher oscillating reaction. Thank
Thank you for
you!
listening.